Thank you, Tony. So I am here to tell you about our biological options and what we would call biofuels. And first of all, I should say that when we talk about biofuels, what we mean is that we're talking about molecules that come from recently living organisms. And the reason that I emphasize recently there is that all of the combustible fuels that we're used to using are in fact biological origin. So petroleum and coal are in fact organic materials that have been acted on by geological forces over many years, over geological time. But originally they were plants and algae whose biomass was in fact transformed. And so when we talk about biofuels, we're talking about biological material that recently came from a living organism, either the metabolites of that organism or the biomass itself. And biofuels have been used by humans for millennia. We can think about burning wood, burning charcoal, and burning dried dung. So these have been common fuels for a long time. In more modern terms, when we say biofuels, we're talking about bioalcohols, biodiesel, biochar, which is the refuse from agriculture, which can be burned to generate electricity, and biogas, which here is shown being collected directly as methane from a cow. So we get biomass from anaerobic digestion of organic material. That anaerobic digestion does occur in a cow's intestine, but it will also happen in a large bioreactor, which is perhaps a more common way to collect that. So one thing that's already been emphasized is that the sun is where we get our energy from. So we can't make any energy, but we can convert it. And there's plenty of energy coming from the sun. The problem is to take that energy and trap it in a way that we can store it and we can use it when we need it is something that we can't really readily do. And for these combustible fuels, like the ones that we've been talking about, what we need to do is we need to have material that is very rich in carbon to carbon and carbon to hydrogen bonds. That's what we have in petroleum, in coal, in wood, in charcoal, and these other materials that we've talked about. And carbon dioxide is quite, oops, keep pushing the wrong button. Carbon dioxide is quite plentiful. It's present in our atmosphere. And what we need to do then is to get it to combine with hydrogen so that we can make these chains, these polymer chains, these carbon to carbon and carbon to hydrogen molecules. But to get hydrogen to combine with carbon dioxide is not something that will happen readily. There's just not as much energy in the starting materials as in the materials that we want to get out. And what's special about plants is that plants are able to take sunlight and use that energy to provide the energy input to condense hydrogen to go together with carbon dioxide so that we can get this organic matter. And once we can get the organic matter in the form of small sugars, then a plant can convert those not only into more complex carbohydrates and proteins, but also lipids and hydrocarbons and some of these materials that we think of as fuels. So why is it that a plant can do this and we can't do it? We were already given the image of there's plenty of sunlight. Can you imagine that we all just go out with a net and we capture what we need for a day? Well, we can't do that because what has to happen is that there has to be some intermediary that can take that sunlight energy and actually do something with it and make a chemical reaction occur. And so what a plant is very good at is that it can, in fact, take in carbon dioxide from the atmosphere. It can soak up the sun's rays and undergo chemical reactions in which it'll end up storing sugars. And the way that it does that is by using a chloroplast that can carry out simultaneously two completely different kinds of reactions, but these two kinds of reactions go together then to get that conversion of sunlight energy into stored chemical energy. And that is that on one hand, there are photosynthetic membranes that have pigments in them that when they absorb light, they can take electrons from water and do two things with them. One is by boosting them to a higher energy level when they absorb light, they can be trapped at a high energy level where they're quite happy to interact with carbon dioxide because now they've been boosted to a higher level. The other thing is that boosted electrons can be passed down electron transport chains where they're used to pump hydrogen, and they can build up a capacitor by getting a pH gradient across a membrane that can be used to drive the synthesis of ATP. Now, meanwhile, in another part of the chloroplast, these high-energy electrons that are ready to interact with carbon dioxide, the ATP that's been made by the pumping of these protons, now can be used to carry out a series of chemical reactions by an enzyme called rubisco, which is the most abundant protein on Earth. It will bind carbon dioxide, and it will take that carbon dioxide and add it to another carbon compound so that you can start taking CO2 out of the air and storing it in a form that we can combust it later. And so fundamentally, that's what plants can do that we can't do. And essentially, all of the organic material that we have on the planet is either because an organism could do this, or an organism ate an organism that could do that, or it ate an organism that ate an organism that could do that. So fundamentally, all of our energy that runs our planet is coming from the sun. Okay, so we need plants, or at least we need organisms that carry out the kind of photosynthesis that plants carry out. And we need them to take that carbon dioxide from the air, use that sunlight energy to let them generate various kinds of molecules that we can use as fuels. And these include fats, from which these long-chain hydrocarbons of fatty acids are useful, isoprenoids in hydrocarbons, various kinds of sugars, polymers, and so various kinds of sugars. Also the biomass itself, which, for example, can be burned or broken down in various ways. And then also hydrogen production, which many organisms, photosynthetic organisms, also carry out. So when we are talking about biofuels, we have first-generation liquid biofuels, which have been around for a number of years. And these are largely ethanol and biodiesel. And in both of these cases, we're taking plant material, either taking plant material that's very rich in sugar, like corn, sugarcane, various kinds of starchy crops, and then using that sugar to feed microorganisms that will ferment it into ethanol. In the case of biodiesel, plant oils, either oils that have already been used as cooking oil and are being reused, or taken directly from various oil-rich seed crops, these fats that are present in the plant oils can be transesterified so that they release these fatty acid methyl esters that are then useful as biodiesel. So both of these kinds of fuels we know how to make. That technology is available. But there are problems associated with them. And one of the big problems that Dr. Mayfield already referred to is that you'll notice that everything that you see here is a food crop. So first of all, if we're going to use these materials to make these fuels, that means that the land that they're grown on is not going to be used for food. The water that's being used to water these crops is not going to be used for food. And so we're taking that land, that water, out of the food supply. And beyond that, with ethanol in particular, there's also another limitation that ethanol is not a fuel that can just go right into into the engines that we have, that we use for our cars and other engines that have been used to using either diesel or gasoline. So ethanol in itself is not very energy rich. It's just this 2-carbon molecule. Biodiesel has a higher energy density, but it still has the problem that we're having to make a trade-off between food and fuel. So when we talk about second-generation biofuels, what I'll be talking about really for the rest of this talk is how do we get away from the limitations that we have with ethanol and biodiesel, and how do we move on to either other sources of the same kinds of feedstocks or completely different kinds of molecules that we can use. Now, in terms of ethanol, as I said, we have the technology. It's really, that's straightforward. Ethanol has been made commercially and industrially for a long time. And you can see that a lot of corn in the US is in fact planted, and you can see in these very dark areas here. In Brazil, sugarcane tends to be used for making bioethanol. And this graph then is showing in blue how the U.S. has really increased its production to the point that we've even exceeded that of Brazil, which has been doing it for quite a lot longer. And a big problem here is that we can make a lot of ethanol, but we make that at the expense of our corn crop going into the food supply. So this is about 40% of our corn that was used to produce ethanol in 2012, and that's 13.2 billion gallons of ethanol. Now, what we do with that as a fuel is we can't just pump it into our gas tank of our car. It's usually blended in the U.S. with gasoline, about 10% gasoline per gallon of gas.